Welcome to my channel. In today's video, we're diving into radio frequency adversarial learning, and we will cover RF signal data collection using GNU Radio, Pluto SDR, and USRP. We'll also explore how deep learning models like CNN, DNN, and RNN play a critical role in distinguishing between trusted transmitters. Let's get started. RNNs have feedback loops in the learning process to determine sequential patterns. RNNs allow a network to maintain information persistence via loops, as with GMMs, Gaussian mixture models, that a given neural network receives an input xt, outputs a value yt, according to a hidden, latent relationship, ht. By passing data through iterative steps in the network, the loop is realized, and hence is recurrent. A RNN applies multiple copies of the same network, each passing a message to a successor as illustrated by unrolling the loop. The RNN chain-like architecture processes a sequential list of data, as shown in Figure 1.1. RNNs can utilize previous information to determine current decisions. All RNNs utilize a chain of repeating modules of a standard NN, such as a singleton layer, as shown in the middle functional block in Figure 1.2. RNNs are useful for learning a sequence of information over a short time interval, over which the gap between the relevant information does not change much, as with the following. 1. A single sensor observing a vehicle conducting a stationary turning maneuver, or 2. A moving sensor observing a stationary target. As the gap between the relevant information time point and the time wherein it is needed becomes very large, RNNs become less accurate. One way to enhance performance is to exploit contextual information in order to mitigate such larger time intervals. Many approaches to radio frequency data seek to develop methods based on DNN and CNNs, while the RNN is implemented with the LSTM or Gated Recurrent Unit GRU. Note that a GRU has fewer gates than the LSTM and thus requires less memory. Since the RNN is designed for 1D signals analysis, the example presented here demonstrates the RNN for RF signals analysis. The radio frequency adversarial learning (RFAL) framework exploits transmitter-specific signatures like the in-phase I and quadrature Q imbalance, i.e., the I/Q imbalance, present in all transmitters by learning feature representations using a DNN that uses the I/Q data from received signals. RF, radio frequency, signal processing is fundamental in modern communication systems. Whether you're working with wireless communication, radar systems, or electronic warfare, the ability to accurately capture and analyze RF signals is crucial. Now, we're going to break down how this process works and how it's enhanced by deep learning. First, let's talk about the RF signal data collection process. As you can see in the diagram, it all starts with generating a random signal. This signal is then modulated using QPSK modulation, a common method in digital communication, via GNU Radio. After modulation, the signal is transmitted through devices like the USRP 9210 or the Pluto SDR, which are popular software-defined radios, SDRs. These devices are versatile and widely used for testing and developing communication systems. On the receiving end, we use an RTL SDR, a low-cost SDR, to capture the transmitted signal. This received signal is then processed using the RTL SDR Python library. The dataset generated through this process is crucial, as it forms the basis for training deep learning models. Now, let's look at the specific parameters used in this setup. The transmitters are configured with a gain of 45 dB, operating at a frequency of 904 MHz in the ISM band, with a bandwidth of 200 kHz. The sample size for each transmission is set at 1024, and the ratio of samples per transmitter ranges from 1 to 8, totaling up to 40,000 samples per transmitter. These parameters are key to ensuring the accuracy and reliability of the data collected, which is then used to train various deep learning models. Let's take a closer look at the experimental data collection. The table here shows different test setups with varying numbers of transmitters, from 1 to 8. The tests use USRP B210 and Pluto SDR transmitters to collect data. The size of the dataset varies based on the number of transmitters, with the largest dataset being 13 gigabytes when using 8 transmitters with an SNR of 10 dB. Such extensive data collection allows for the development of robust deep learning models that can distinguish between different transmitters, even in the presence of adversarial conditions. After the data is collected, it's time to classify the transmitters using deep learning models. The models used here include CNNs, convolutional neural networks, fully connected DNNs, deep neural networks, and RNNs, recurrent neural networks. The RNN is particularly powerful as it incorporates LSTM, long short-term memory, and GRU, gated recurrent units, which are effective in handling sequential data. These models can accurately distinguish between up to 8 different trusted transmitters, even after eliminating adversarial ones. This capability is crucial in environments where secure and reliable communication is essential. RF signal data collection combined with deep learning offers a powerful approach to signal classification and transmitter identification. Whether you're working in communications, defense, or research, understanding these processes is essential for developing advanced systems. In the previous slide, we discussed how RF signal data is collected using GNU Radio, USRP, and Pluto SDR. Now, we're moving forward to the classification of these signals using various neural network models. Specifically, we'll be looking at deep neural networks, DNN, convolutional neural networks, CNN, and recurrent neural networks, RNN. Let's start with the deep neural network, or DNN. The DNN in this setup consists of several dense layers, each followed by a dropout layer to prevent overfitting. As you can see, the network begins with an input layer that takes in the process signal data. This input is then passed through multiple dense layers, each using the TAN activation function. Dropout layers with a dropout rate of 0.5 are interspersed to ensure that the model generalizes well and doesn't memorize the training data. Finally, the output layer uses a softmax activation function, providing a probability distribution over the possible classes. In this case, the different transmitters. The DNN is relatively lightweight, with 6.8 million parameters, and achieves impressive accuracy with relatively low computation time. Next up is the convolutional neural network, or CNN. CNNs are particularly well suited for processing data that has a grid-like topology, such as images or, in our case, RF signal data represented as 2D matrices. The CNN here consists of 3 convolutional layers, each followed by a max pooling layer to reduce the spatial dimensions. After the convolutional layers, the data is flattened and passed through fully connected layers, similar to the DNN, before making the final classification decision. The CNN has a significantly higher number of parameters, 38 million, but this comes with a trade-off in computational time, especially when classifying 8 transmitters. Lastly, we have the recurrent neural network, or RNN. RNNs are designed to handle sequential data, making them ideal for time series data like RF signals. This particular RNN uses LSTM, long short-term memory, layers, and GRU, gated recurrent units, both of which are effective in capturing long-range dependencies in the data. The RNN architecture in our example starts with an LSTM layer, followed by a GRU layer. These layers help in retaining important information over time, which is crucial for accurate classification. The network also includes dropout and batch normalization layers to enhance performance and stability. Now, let's compare the performance of these models, as shown in the table. The table provides an accuracy comparison of these neural network approaches for classifying 4 and 8 transmitters. For 4 transmitters, the CNN has the highest number of parameters at 38 million, but achieves an accuracy of 89.07% in approximately 25 minutes. On the other hand, the DNN, with just 6.8 million parameters, achieves an impressive 96.49% accuracy in just 12 minutes, making it a more efficient choice. When the number of transmitters increases to 8, the CNN's accuracy drops to 81.59%, and the computation time rises to around 30 minutes. The DNN remains consistent, with a slight drop in accuracy to 94.6%, but the RNN models, particularly the GRU-based one, show their strength with an accuracy of 97.06% in about 16 minutes. This comparison highlights how different architectures can be leveraged based on the specific requirements of the task at hand, whether it's speed, accuracy, or computational resources. In conclusion, Each neural network architecture has its strengths and weaknesses when it comes to classifying RF transmitters. The DNN offers a balance between accuracy and efficiency. The CNN excels in tasks that require processing of spatial data, and the RNN shines in handling sequential data. Your choice of model will depend on the specific needs of your application. This content sourced from Deep Learning for Radar and Communications Automatic Target Recognition book. Thank you and meet you in next video. Bye.